Given a sequence of token embeddings, a typical transformer architecture processes them using a stack of attention and mixture of experts layers. But a deep network is difficult to train. A common strategy is to use residual connections. Let's see why it works. The input token embedding has size t by d, where t is the sequence length and d is the embedding dimension. We label these layers as F1, F2, and so on. So with residual connections, we compute the input to the second layer, H2, by adding the input to the first layer, H1, and the output of the first layer, F1 of H1. The skip connection carries the original input forward unchanged. Let's expand this recursively. Here, the input to the third layer, H3, equals H2 plus F2 of H2. If we substitute the expression for H2 from the first equation, we see that H3 becomes H1 plus F1 of H1 plus F2 of H2. One more time. Here, H4 equals H3 plus F3 of H3. By substituting the expression for H3, we have this equation. Hopefully, you can see the pattern now. The representation at any deeper layer L is the representation at a shallower layer L plus the sum of all transformations between them. Look at the gradient flowing back to an early layer. There are two terms, one via the skip connection and one via the transformation blocks. The skip connection path is direct, without multiplication and attenuation. No matter how deep the network gets, there is always a clean highway for gradients. As a result, residual connections help alleviate the vanishing gradients problem and enable the training of very deep models. But there is a challenge. Modern transformers use pre-layer normalization to stabilize training and make optimization easier. But every layer adds a correction on top of the previous output. This accumulation causes the magnitude of representations to naturally grow with depth. Consequently, each layer's contribution shrinks relative to the growing residual stream. The deeper layers are thus forced to produce outputs with larger magnitude even when the inputs are all normalized. The gradients become imbalanced. Deep layers receive small gradients, while early layers receive relatively large gradients. The imbalance leads to ineffective use of network depths. This problem is known as pre-norm dilution. Furthermore, let's look at the residual connection equation again. Each new layer sees only the representations HL minus 1. Everything that happened before has been compressed into a single vector. Information is irreversibly lost at every step. This may remind you of sequence modeling methods such as recurrent neural networks or LSTMs. Here, to process a sequence, we start with the empty state H0 and iteratively update the hidden state. For each new input x, we use a function fw that maps x and the previous hidden state to produce the next hidden state. The hidden state ht is a compressed summary of everything the model has seen so far. The bottleneck makes it challenging to process long sequences effectively. This is where attention comes in. Instead of compressing the history into a single hidden state, each output dynamically attends over all relevant inputs. No bottleneck, no forgetting, no information loss. Now, if we rotate the residual networks by 90 degrees, we see that it has a similar structural bottleneck. Each layer only sees the single output of the previous layer. Can we improve residual connections in the same way that attention improves recurrent neural networks? That is the core idea of attention residuals. Let's build attention residuals from the first principle. We start with the embedding feature H1 and the transformer architecture with layers F1, F2, F3, and F4. With standard residuals, we add the embedding h1 to the output of the first layer f1 of h1. This gives us h2, the input to the second layer. Implicitly, we are using a fixed weight of 1. But can we make these weights learnable and data dependent? Alpha 0 to 2 controls the amount of h1 that contributes to layer 2. Alpha 1 to 2 controls how much f1 of h1 contributes. To compute these data-dependent weights, we use attention. We start with a per-layer query vector Q2 and compute the compatibility scores between the query and the two key vectors. We then normalize the scores using softmax so that they sum up to 1. These are the weights alpha 0 to 2 and alpha 1 to 2. Finally, we produce the output by linearly combining the value vectors using the weights. Here, the query vector is a trainable d-dimensional parameter W2 per layer. The keys are the embedding h1 and the first layer output f1 of h1. Same for the value vectors. Typically, we use the vector dot product to measure the compatibility score between the query and key vectors. But the magnitudes of different layer outputs can vary widely. Therefore, we need to normalize the key vectors before computing dot products. Now, let's see how we compute h3. Here, we need to compute 3 attention weights for the input h1, f1 of h1, and f2 of h2. Similarly, we use the query vector for this layer and the key vectors to compute the attention weights. The key vector k2 and value vector v2 both come from the output of the second layer f2 of h2. You get the idea? Every layer is a learned weighted mixture of all the outputs that came before it. Here is the general equation. The attention weights are computed by the vector dot product between the query vector and the normalized key vectors. The key and values vectors are just the layer outputs. One important implementation detail is that we initialize these per-layer trainable query vectors to 0. It ensures that at the beginning of training, the attention is just a simple uniform average, which closely resembles standard residual connections. Compare attention residuals side by side with standard residuals. The structure is identical. The only difference is that every fixed one is replaced by a data-dependent attention weight. Let's see some results. Attention residuals reach a lower validation loss than the residual connection baseline. The training dynamic becomes more stable. As discussed earlier, the magnitude of layer outputs naturally increases with depth due to accumulation at each layer. Attention residuals address this by using attention weights that sum to 1 to prevent unbounded accumulation. As a result, the gradient magnitude becomes more balanced across all layers. This approach is called full attention residuals. Full attention residuals require all layer outputs to remain alive during both the forward and backward passes. This is fine for training small models. The activations are already saved for backpropagation. But modern large-scale training uses 2 techniques that break this. First, memory. To reduce memory consumption, we only need to store the activations at a small set of layers and recompute them for backpropagation. But full attention residuals require all previous activations from the forward pass. This suggests that each layer's output must remain in memory until the end of the forward pass. Second, communication. Training large models requires distributed training across multiple GPUs. But with attention residuals, every layer output must be transmitted across devices, resulting in significant communication overhead. Therefore, we need a smarter design that preserves the benefits while managing the cost. Let's first visualize the full attention residuals. Here we have a transformer with 12 layers. To compute the input to the I layer hi, we need to linearly combine the outputs of all the previous layers. But perhaps we don't need individual layer-level resolution. This is the idea of block attention residuals. We compress groups of layers into single summary vectors. We refer to the input embedding as B0. Layers 1 through 4 form block 1. Layers 5 through 8 form block 2. Layers 9 through 12 form block 3. Each block summary stores the summation of the layer outputs within the block. Now, to compute H9, instead of attending to every layer output, we only attend to a smaller number of compact block summaries. This is great, but there is a subtlety. The current block is still under construction. For example, layer 10 is inside block 3. At this time, block 3 is only partially complete. To compute H10, we also need to consider the partial summary of block 3. Here we denote that partial summary as B31. In this case, it's the output of the 9th layer, F9 of H9. To compute H11, in addition to attending to the summary of previous blocks B0, B1, B2, we also attend to the partially accumulated sum for the current block. Same for computing H12. This accumulation happens online during the forward pass. No extra storage required. Look at the scaling curves. Attention residuals consistently outperform baselines across all model sizes. With just 8 blocks, block attention residuals recover nearly all the performance of full attention residuals. The paper reports a 1.25 times compute advantage over standard residual connections. In other words, attention residuals reach the same loss at 20% lower compute costs. Now look at the effect of block size. Without only one block, performance is poor, too much resolution is lost. As blocks increase, performance improves consistently. In practice, the authors choose 8 blocks for infrastructure efficiency. The authors visualize the depth-wise attention distributions. The top row shows full attention residuals. The bottom row shows block attention residuals. The columns correspond to pre-attention and pre-MLP layers. First, each layer attends most strongly to its immediate predecessor. This shows up as a strong diagonal pattern. But we still see selective off-diagonal patterns, suggesting that the model leverages skip connections. The attention weight distribution in block attention residuals follows a similar structure. This is great, but to scale up the model training, we need an infrastructure design for efficient training and inference. Large models with tens of billions of parameters do not fit on a single GPU. To train these large models efficiently, we have to split them across many devices and coordinate their computation. There are strategies that cut the model along a different dimension. For example, data parallel cuts up along the batch dimension. Each GPU gets a different subset of training examples and runs the full model on its subset. All GPUs run at the same time, and gradients are averaged across devices after each step. Tensor parallelism splits along the width dimension, distributing individual weight matrices across GPUs. Pipeline parallelism cut along the depth dimension. Each GPU holds a contiguous group of layers as a pipeline stage. Data flows down the pipeline. Each GPU processes its layers and hands off to the next GPU. Communication only happens at stage boundaries. This is the approach most relevant to attention residuals. Let's see how it works. Here we have a 16-layer transformer model. We split these layers across 4 GPUs. GPU 1 runs layers F1 through F4. GPU 2 runs F5 through F8. GPU 3 runs F9 through F12. GPU 4 runs F13 through F16. Now let's trace through a single training step. GPU 1 runs the forward pass and sends its output to GPU 2. GPU 2 waits, receives, computes, and sends to GPU 3. GPU 3 waits, receives, computes, and sends to GPU 4. GPU 4 finishes the forward pass and starts the backward pass. The backward pass flows in reverse. GPU 4 to GPU 3, then to GPU 2, and finally to GPU 1. After a forward and backward pass, we can update the model parameters. But look at what GPU 1 is doing while the other GPUs are running. Nothing. In a naive schedule, most GPUs are idle most of the time. These idle gaps are called pipeline bubbles. A simple approach to reducing pipeline bubble size is micro-batching. Instead of one large batch, we split it into m smaller micro-batches. As soon as GPU 1 finishes micro-batch 0, it immediately starts micro-batch 1, without waiting for the full forward pass. GPU 2 can then start processing micro-batch 0, while GPU 1 is on micro-batch 1. Micro-batching improves pipeline occupancy. But each stage is still a large chunk of the model. Our scheduling is too coarse. Therefore, we need to partition the model with finer-grained stages. Instead of each GPU holding one contiguous block of layers, each GPU holds multiple non-contiguous groups, called virtual stages. Here, GPU 1 holds layers F1 and F2 as virtual stage 0, and layers F9 and F10 as virtual stage 1. GPU 2 holds F3, F4 as virtual stage 0, and F11, F12 as virtual stage 1. Data flows through VS0 first. GPU 1, 2, 3, 4 each run their first set of layers. The output then travels back to GPU 1 for VS1 and then completes the second set of layers. Combining interleaf scheduling with micro-batching, we see that we substantially reduce the pipeline bubbles and memory peaks. Now, how does this work for standard residual networks? We start with the embedding H1, process the first two layers to produce F2 of H2. We then transfer this output to the second GPU and process the two layers to produce F4 from H4. We repeat this process until all the layers in the forward pass are completed. Notice that we only need to transfer a fixed size hidden state from one stage to the next. But what happens when we use block attention residuals? Let's see what additional data we need to transfer across stages. We start with the input embedding B0. For the second GPU, in addition to the hidden state, we also need to transfer B0 from GPU 1 to GPU 2. As each block consists of 4 layers, after processing F3 and F4, GPU 2 produces a block summary B1. Following the same process, we transfer both B0 and B1 to GPU 3. After processing F5 and F6, the GPU 3 needs to transfer the B0 and B1 from GPU 3 to GPU 4. Then, after processing F7 and F8, the GPU 4 produces a block summary B2. Now that we have completed the first virtual stage, we need to circle back and transfer the data back to GPU 1. But here you can see the problem. The interleave schedule does function as intended. However, when using block attention residuals, each block must attend to the summaries of all preceding blocks. As a result, whenever data crosses between GPUs, communication overhead increases significantly because block summaries must be transferred along with the hidden states. But if we look closely, we see that on GPU 1, we already have B0 from virtual stage 0. Similarly, on GPU 2, we already have B0 and B1. This means we do not need to transfer the redundant block summaries across the GPU by caching and reusing them. We can simply reuse them directly. This is called cross-stage caching. In our example, we reduce the number of block summary transfers across GPU boundaries from 19 to 11. A 42% reduction in cross-GPU communication overhead. By increasing the number of virtual stages, we can further reduce communication overhead. This is great. But how about inference? Let's review the computation of block attention residuals. To compute the last block, we need to compute the attention weights over the available block summaries and the partial sum of the current block. Doing so for each layer incurs excessive memory access. Let's see if we can make the computation more efficient. Here, the rows W9, W10, W11, W12, one learned query vector per layer. The columns are the available key vectors, B0, B1, B2, and the partially accumulated B3. But not all entries are valid. For example, computing H9 cannot use B3 at all, as we haven't processed the layers in the third block. Computing H10 can use B31 with the partial sum to layer 9. Computing H11 can use B32 with the partial sum up to layer 10. And so on. We then apply softmax on these valid scores to produce the attention weights alpha. Finally, we combine the value vectors using the attention weights to get the outputs H9, H10, and H12. To compute this efficiently, we have a two-phase computation strategy. As these query vectors are learned parameters that do not depend on current activations, we can compute the attention scores and weights with batch matrix multiplication. This is phase 1. In phase 2, we sequentially compute the attention involving the evolving partial sum. These two can then be merged efficiently with online softmax. These infrastructure designs enable large-scale training of models with full and block attention residuals. Here are the results based on the full Kimi-linear 48B models. The block attention residual model improves over the baseline across all benchmark evaluations. The improvement is particularly salient for multi-step reasoning tasks. There is a second finding just as interesting. Given a fixed compute budget, what is the optimal model architecture? Compared to the baseline, attention residuals prefer deeper, narrower networks. Given the same parameters, attention residuals benefit more from adding layers than from increasing widths. With standard residuals, simply stacking additional layers eventually yields diminishing returns. Each new layer's contribution becomes increasingly diluted by the accumulated residual stream. In contrast, attention residuals can make much more effective use of network depths. Before you get too excited, it's worth noting that the idea of giving deep layers access to earlier representations is not at all novel. There have been many attempts. For example, each layer concatenates all previous layer outputs and passes them through a convolution. This gives us dense net. Instead, we can learn aggregation weights for each layer. This gives us the dense former. We can make this more flexible by making the combination dimension-dependent and input-dependent with a learn per layer weight vector W. This gives us the deep cross attention. It's similar, but the input-dependent components involve only a vector dot product without softmax attention. As we can see, these are not new ideas. But the interesting part of this paper is its solid implementation. In particular, the infrastructure design enables large-scale training to really demonstrate the strengths of attention residuals with minimal overhead. Thanks for watching, and I'll see you next time.